Hey guys, welcome to another video. We're going to be going through the topic of motion, which is the second part of general physics. So this is just a quick summary of the points that we'll hope to cover today, and we'll take a look at the first section here, which is to do with speed and velocity. So you've probably heard and you are familiar with the idea of speed, which is just how quick you are or how fast you're going. And so if you were to put it into mathematical terms, speed is simply just the change in distance per second. A fast object just happens to cover more distance per time unit than a slower object, right? So therefore the formula for speed is the total distance divided by the total time. So that should make fairly good sense. For example, if you did a 100-meter race and you finished in 10 seconds, your speed would be 100 meters divided by 10 seconds, which would give you 10 meters per second. Meters per second is the unit for speed and velocity. So speaking of velocity then, what is velocity? Well, velocity is actually the change in displacement per second, and the concepts between speed and velocity is very similar, but also very, very important to distinguish. Now, the question then becomes, well, what is distance and what is displacement? And what's the difference between the two? So the main key difference here is that displacement actually takes into account not only just the pure amount of distance, but also the direction of travel as well. So what seems to be a very good example here is if you imagine point A down below there and you imagine point B, the difference between point A and point B is, say, 500 meters. And let's just say that your starting point is A, right? So you start at A and then you walk to B, and from B you walk back to A. So the total distance that you've covered would be 1,000 meters, right? Because walking to B takes 500 meters and walking back to A is another 500 meters. So the total distance is 1,000 meters. So according to the formula of speed, 1,000 meters divided by, imagine you took 200 seconds, 2,000 seconds to get that trip done. Imagine then the speed would be 1,000 meters divided by 2,000 seconds, which would give you 0.5 meters per second. Okay, so that makes sense. Now, displacement is actually a little bit more different because, as I said before, displacement actually takes into account the direction of your travel as well. So going from A to B is 500 meters. Okay, so that's in a certain direction, right? You're traveling, let's just imagine a compass, and so you're traveling east, okay, 500 meters. Now, when you travel from B back to A, what it means is that you're traveling in the complete opposite direction that you came from. So essentially, what it means is that we're going to take the initial distance of 500 meters, and we're going to call that positive 500. And when you go back the other direction, because it's going in the opposite direction, we're going to put a negative sign on top of that. So essentially what it means is 500 meters positive going to the right and minus 500 going to the left. And when you get that, it sort of cancels out and you get an overall displacement of 0. Another way of thinking about it is, well, ignore the total journey. The total journey doesn't matter. What's really important really in terms of displacement is how far off you are from your original starting point. So if you started at A and you end up back at A, your overall displacement, the amount of change from starting point to end point, is 0. You haven't actually moved anywhere if you consider starting from A. And so therefore, that's another way of thinking about the fact that if you go from A to B and B to A, the total displacement would be 0. So therefore, since velocity is displacement divided by time, what you get is actually 0 divided by 2,000 seconds. So despite the fact that your entire journey was 2,000 seconds, you actually have had no displacement, or you have had no velocity as a result of that. Okay, so I hope that makes sense. So acceleration is a term that you would use to define the change in velocity per second. Okay, so for example, if something is speeding up, Okay, going from 100 meters per second to 200 meters per second to 300 meters per second, you can gradually see that it is speeding up, and that speed up is what we call acceleration. And how quickly something speeds up is essentially what the term defines. So acceleration in mathematical terms is change in velocity divided by the time taken for that change to occur. Now, positive acceleration is when an object increases in velocity over time, which is, for example, you have a car at the starting line and then it starts to accelerate. That is what we know as positive acceleration. But an object can also decrease in in its speed as well. It can go from 100 meters per second all the way down to 0 when it comes to a stop. Now, that is sort of a negative form of acceleration, which is, of course, when the object decreases in speed over time, or decreases in velocity over time, and we call that, in other words, deceleration. So these are very, very important terms we've covered so far. We've covered the idea of speed, we've covered velocity, and we've covered acceleration. Just to sum it up, speed is just distance over time, velocity is displacement over time, and acceleration is the amount of how quickly velocity is changing over time. In other words, change in velocity divided by the time taken for that to occur. So, as we know now that acceleration is the amount of change in velocity per time unit, let's think of something, an object, say, falling just on Earth as a result of free fall. So, like, imagine you throw something off a cliff, and obviously that object is going to fall down. And, just from looking at it, you'd find that the object gradually increases in speed, it drops quicker and quicker and quicker as it falls down the cliff, right? And that is the acceleration of the object due to the gravitational pull of the Earth's gravity. So any object that's falling in the presence of the Earth's surface will be pulled specifically by a constant acceleration of 9.8 meters per second. Okay, so that's a constant value. No matter what you throw off a cliff, it will fall at an acceleration rate of 9.8. Now, over time, what tends to happen is that the acceleration starts to drop and the object starts to fall at a constant speed. Right, the reason for that is because the air resistance starts to oppose the acceleration that the gravity causes. So eventually the downward force of the gravity gets cancelled out by the force of air resistance, which pushes it upwards. So eventually the object will start to stop accelerating and it will start to fall at a constant velocity, and we call that terminal velocity. It might be easier to take a look at it on this whiteboard. Let's just imagine a big cliff here, and you throw a ball off the cliff. What will eventually happen is that the ball will start to accelerate downwards, and as I said before, it accelerates at 9.8 meters per second squared. So the ball will start to accelerate downwards as a result of the gravitational force of gravity. But what tends to happen is that the acceleration starts to slow down over time. And in a perfect world with no resistance, it'll just accelerate at a constant rate of 9.8 forever, pretty much, until it hits the ground. But the reality is not like that, where we have air. And what happens is that as the object starts to gain speed from acceleration, what also increases is the resistance going upwards, which is air resistance. So air resistance is the force that pushes it upwards, and the force that's sort of accelerating the ball downwards is going to be, as I said, the gravitational force. So as the object accelerates more and more and more, speeds up more and more, as the ball starts to increase in speed as a result of the acceleration, the air resistance starts to increase. And eventually what happens is the gravitational force gets cancelled out by air resistance, right? The force is equal. And as you'll learn when it comes to the nature of forces later, just because the forces cancel out doesn't mean the ball just suddenly stops. What it does mean is the ball stops accelerating. The ball is still falling, but it's falling at a constant rate. It's not actually speeding up anymore. And when that happens, the ball will just drop at a constant rate without speeding up as it falls, and that is what we call the terminal velocity. So I hope that makes sense. Now, as we take a look at the idea of displacement and velocity and all that, we come across these various graphs. The very first graph we'll be looking at is the displacement time graph, which is simply a graph to show the displacement per time unit. And so here, if we take a look at this particular displacement time graph, you need to be able to interpret what's going on here. So if you take a look at the first part right over here, you can see that the displacement goes up and up and up and up until this sort of 6-second mark here. What that means is that over the time of 6 seconds, you're getting a change in the displacement of this object. So remember, the displacement over time gives you the value of velocity, which in this particular graph, you can figure it out by measuring the gradient of the particular region you're looking at. And the gradient is simply what you would calculate as the change in y-axis divided by the change in x-axis. So for this particular time frame from 0 to 6, as the displacement goes up from 0 to 10, if you wanted to calculate the speed of the object in this particular region, you would just need to look at the gradient, which is the change in y-axis. So the change in y-axis is 10 because it went from 0 to 10, divided by the change in x-axis, which went from 0 to 6. So if you were to do those calculations, you would find that you'd get 10 over 6, which will give you 1.67 meters per second, which happens to be the velocity of this object in this given region. Now, between the region of 6 seconds to around 11 seconds, you can see that the displacement is just a straight line. What does that mean? It means that there's no displacement, which means that the object is stationary. It's not moving at all. It's just sitting there. And as you make your way over to this right-hand side part of the graph, you can see that the displacement starts to go downwards. What that means is the object is sort of going back to its original position. Remember, because displacement starts to go downwards as you go closer to your original starting point. So you can see that the object is returning to where it had originally started from, and you can see that the line isn't a straight line. What that means is the velocity is not constant, right? Because the gradient of each particular region of this wiggly line is going to be different because, again, it's not a straight line. So when you see that the line is not straight, you can tell that the object is not moving at a constant pace. So I hope that makes sense. Key points: if it's a straight line, it's moving at a constant pace. If it's a straight horizontal line, like this middle area there, it means it's not moving at all. If you see a line that is wavy, that means that the object is moving at a certain speed that seems to be changing over time. Okay? The other graph that we need to look at is the speed time graph. A speed time graph pretty much plots the speed on the y-axis and the time on the x-axis. So here, there's various things that you can take note of. Now, if you have a speed and time graph, you can actually calculate the distance that is traveled in a particular region by calculating the area underneath the graph. So if you take a look at this particular graph down below here, you can see that there is a certain change in speed over this time frame, right? And what you can do is the shaded area here, that is the area underneath the region of the graph that you're trying to calculate the distance for. And so remember, the area underneath a triangle is just going to be half the base times the height. So if you were to use that calculation, you'd be able to figure out the amount of area that's present underneath the region you're looking at, and that will actually give you the amount of distance that the object traveled in the particular region that you are looking at. And the acceleration can actually be calculated by calculating the gradient of the region. So again, the gradient is the change in y-axis divided by the change in x-axis. And if you were to calculate the gradient of a particular part of a speed-time graph, the result of that calculation is going to give you the acceleration of the object in that time frame. So those two things are very important for you to know, because in an exam they might give you a graph and they might get you to calculate these things, and so you need to know how to do that. Here we're just going to take a look at various speed time graphs and sort of interpret what's happening. So here is an example of a car that's accelerating until it reaches its maximum speed. So as you can see, initially there is a fairly steep gradient, right? What that means is, remember, gradient is acceleration. It means that the car starts with its greatest acceleration, meaning its steepest gradient at the start of the graph here, and eventually you'll find that the line sort of plateaus horizontally. And if it's a horizontal flat line, what does that mean? It means the speed is not changing. It doesn't mean that the speed is zero, because again, it's still high up on the y-axis here. It just means that the speed isn't changing. What that means is that the speed is constant, and that also defines the acceleration as being zero. No change in speed means there's no acceleration, okay? So it means that the car reaches its maximum speed and stays there for a certain period of time, which also means that the car is not accelerating, okay? And a runner who accelerates with a constant acceleration gets to maximum speed and steadily decreases to a complete stop. This is what this graph suggests. So let's take a look at how that is the case. Now, at the start here, you can see that the speed increases steadily. We know that it increases steadily at a constant rate because it's a straight line, right? So it's a straight line going upwards, meaning that there is a constant level of acceleration happening there. Now, eventually, the line results in a horizontal sort of plateau in this middle section here, which means, again, speed is not changing, it's constant, meaning acceleration is zero. So the runner has reached their maximum speed and is not going up any longer, and is simply maintaining their maximum speed for a certain period of time, and eventually you start to find that the speed starts to go downwards, meaning that the runner is essentially losing speed, and therefore they are decelerating, eventually coming to a complete stop, which is when the speed hits zero right at the end there. Now, last one is an example of a skydiver from the time that she jumps until the time she reaches the ground, including the point at which she opens a parachute. So initially you can see that there is a very steep level of acceleration happening. Now, is the acceleration constant? No. The reason for that is because clearly you can see that this segment where the speed starts to go up is not a straight line. It's curved, and when it's curved, it means that there is the speed is not constantly going up at the same rate, which also means that acceleration is not constant and is changing. And the reason why the acceleration is changing is something that we talked about before, because when the jumper jumps off the plane, initially they are going to be pulled by the surface of the earth by gravity, and they will start to accelerate at 9.8 meters per second, or 9.8 meters per second squared. What that means is they start to fall at that level and they increase in speed by 9.8 every second. But eventually, the air resistance will start to push them upwards, and they will start to lose their speed, or they will start to lose the acceleration. So, and as I said before, therefore the acceleration seems to not be so constant eventually, and it starts to sort of decrease a little bit as a result of air resistance. And then at some point the parachute will open up, and there's that sudden amount of huge deceleration that occurs when you suddenly open the parachute. And so again, when they open the parachute, the deceleration isn't constant because you have that curvature of the graph occurring in that middle section. And eventually, as they fall below with the parachute open, the speed eventually levels out. And the speed eventually levels out as a result of what we call terminal velocity, when the gravitational pull becomes pretty much equal to the air resistance, the force that pushes it upwards. And so the speed at which you're going down or free falling seems to stay constant, which is signified by this flat line here, and the speed remains constant during this period. So that's an important concept to understand. So I hope that was helpful. That was quite a lot to go through. Any questions, feel free to just comment down below and I'll try to help you out. For those of you guys that are interested, feel free to have a look at my Patreon channel, where I'm just adding various resources here and there. Once I finish the entire physics syllabus here on YouTube, I'll probably go through past papers. I have already done so for a lot of the biology and chemistry, so for those of you that are taking that, you might want to check that out. Otherwise, I will see you in the next video.